it goes up in proportion to that current squared. Is that okay? Not only does that mean the wire gets hot, it means that things don't work very well. So I have so many demonstrations up here. Let me show you first. Battery, 12-volt battery, of course you know that guy, and a light bulb. And if I plug in the light bulb, it lights up nicely. This was fine. You know, in 1880, you want to have a light bulb to show off all your friends. Great. You had the battery, you had the light bulb. You might put the battery in the basement, but anyway, local circuit. How about if you want to run a distant light bulb, you make a bigger circuit. So I've got two wires here. I better plug on that end first before I plug in this end, make sure I've not got things set to start a fire. All right. So now the light bulb, instead of being right near the battery, let's take the battery off down the block and put the light bulb in your house, put the battery down the block, and we plug it in, and now the circuit is much longer. Oh, well, that's disappointing. The local light bulb is nice and bright. These are identical light bulbs. The distant light bulb is pretty dim. How come? Well, because that light bulb wants a fair amount of current to get hot. It actually wants 7 amperes. Remember we did this the other day. It wants 7 amperes to flow through that wire. Well, that wire actually was never meant to be carrying electric power. It's more like for speakers. Although, you know, even in speakers, they carry electric power. This wire being very long, I don't know, it's 100 feet or something like that, a very thin wire, 100 feet out, 100 feet back. There's a pile of it on the table. It's so thin that its electrical resistance is pretty big. And if you try to send anything near 7 amperes through it, it's going to charge a lot. It's going to experience a big voltage drop. And so what's showing up at the entry of that light bulb, and the far light bulb, unlike this one's getting almost full 12-volt arrival. That one's getting like 7-volt arrival or 8-volt arrival. About 4 volts are wasted getting over to that light bulb. And you've got another 4 volts in the light bulb, which is why it's so dim. It's not designed for 4 volts. It's designed for 12 volts. And then you need the last 4 volts for the current to struggle its way back to the battery to pick up more power. So Edison was facing this kind of problem. If you put the power station right near, the power generating station right near the consumer, you're good. Any old wires will do. If you put the power generating station far from the consumers, even like a mile or 2 away, you've got this energy waste problem. You can't get the power to the consumer without losing a lot of its initial voltage and power, and same on the way back. Any questions about why that bulb is dim? You got it? Most of the power is wasted in the wires. So what was Edison's solution? Well, his initial solution was, well, one is to have not one power generating station for all of New York, but rather many of them, within reason. And the other was to use really thick wires. Because according to that relationship, the last relationship there is the power being wasted, it's equal to the resistance times the current squared. If the current's a problem, that is, you can't make it any smaller than a certain value because you need to deliver that much power, what's your choice? Well, use low resistance. So clearly, keep the wires as short as they can be, but if you've got a mile distance to travel, it can't be any shorter than a mile. And the other thing to do is use the best conductor you can afford, which is probably copper. During that era, aluminum was extraordinarily expensive in that era. It was a rare metal at that point. They hadn't figured out how to make it, really. So use copper, and you made it as thick as you could. So instead of using these really wimpy wires, let's use much heavier wires, a lot more copper in them. So they're super highways for electric current. And now we're in good shape, right? Problem solved. Oh, come on. What did I plug in? I plugged in the wrong wire. nah, I don't really have a solution to this. I don't have the right plugs. What I'm trying to show you is the two bulbs are pretty nearly identical now. Okay, so yeah, I do have a solution. There's the solution. Dum. I would say it's a long week already, but it's a long month, probably a long semester. Okay, so the solution here is that those wires now have such little resistance that they're able to carry this kind of current, the 7 amperes of current that bulb wants, while losing very little energy per charge. So the voltage drop now in those wires is much smaller. Problem is those wires are much more expensive. In this case, well, we can afford the difference between these wimpy little wires and those thick wires. If you're really trying to electrify a city, it becomes a serious problem. You're buying a lot of copper. And that was really finally just debilitating for Edison Electric. As a side note on this, there's another interesting case. This is a public service announcement. I'm getting my public service announcement box. Jumper cables. Many or nearly all of you at some point or other will have either a dead battery or when something's gone wrong with your battery and your car won't start. Familiar problem, right? And the classic solution to that is to get a second car involved with a second electric circuit. Your car has an electric circuit in it that when you're starting your car, what's going on? You're creating an electric circuit containing a battery, your car's battery, and a motor. The motor is the starter motor. It spins your engine, gets it going. But that's basically the circuit. And current flows from the high voltage end of your battery through the starter motor to the low voltage end. If your battery's dead, it's for all practical purposes the circuit is incomplete. There's no battery in it. So what do? You get another car involved that has the same kind of circuit. They don't use their starter. They may run the engine, which helps. It supports the battery with the generator. But basically, it's the car's battery that you want primarily. You want to connect that car's battery to the circuit in your car. You want its positive terminal connected to the positive terminal of your battery, and its negative terminal connected to the negative terminal of the battery. So the two batteries are working together to drive current through your starter motor. Both positives together, both negatives together. Technically, you make the final connection not by touching the battery, but by touching something that's connected to the battery, just to keep the sparks away from the physical battery, because the battery actually can have hydrogen gas around it. You can ignite the hydrogen, which is not good. So you're making a bigger circuit. If you ignore the presence of your car's dead battery, which is you don't really want to ignore it, but let's set it aside. Really, the circuit now is their car's battery. The positive terminal thereof goes through these jumper cables and through the electrical wiring in your car to the starter motor, delivering power, and then that same current returns through the electrical structure in your car, and then through the jumper cables to their battery. You can picture the circuit. The circuit now involves the jumper cables, two wires, of course, one delivery, one return. When you go shopping for those, if you ever go shopping for those jumper cables, they'll sell you a whole variety pack of different choices. And if you try to go cheap, what you will get is 2 clamps, one on each end of the jumper cable, of each cable. Of course, there are 4 clamps total. And the thinnest wires you can imagine, just rinky-dink wires, like these guys. They will not let large currents flow without charging a lot of voltage drop. And you can tell the cables don't have enough metal in them because they're too light. So these light, fluffy things, you can just throw them in the back of the trunk of your car. It's great. Wow, I got jumper cables. I'm safe against all the trouble. When you try to use them, you'll discover that they don't deliver enough current. They barely will. Maybe they'll start your car, but could easily not. The really good jumper cables have very heavy copper wires in them. They carry current with charging very little in the way of wasted energy, and much better for starting your car. So if this ever happens, you go shopping for jumper cables, be skeptical of the ones that are too cheap and too light. Not enough metal. The currents that the cars need to start, particularly in cold weather, when the oil in your engine is almost like molasses. They need hundreds of amperes flowing through those wires. And wires like, this wire will simply catch on fire if you try to get 100 amperes to go through it. These guys, pretty much the same. 100 amperes, they need a wire that's like as thick as your little finger to really be effective. Okay? Off my soapbox. So back to these guys, and now we've got no light over there. Who knows? Did we burn the bulb out? Nope, it sprung free. Okay, so Edison was in trouble. He was having difficulty conveying power, even in the relatively local distances he needed in order to electrify New York City. Trying to do it by simply sending more and more and more current was not working very well. Well, if you think about how, I'll stop this, everything's dazzling. If you think about when you deliver electric power, you can, when you deliver the power that's consumed finally by a light bulb or anything else is the product of two things. It's the amount of current that flows through the light bulb, that's the charges per second, times how much energy each charge drops off, which is a measure of the voltage drop, measured by the voltage drop in the appliance. So if you have a light bulb and you want it to consume 100 watts, it needs 100 watts to be bright. You can provide that 100 watts with 100 amperes and a 1 volt drop. So a huge current with a tiny voltage drop, meaning every charge shows up with very little energy, just enough, drops off one volt worth, and then returns. So huge current, little voltage. Or you can use a bigger voltage and a smaller current. You can also deliver 100 watts to the light bulb by sending 1 ampere of current through the light bulb, but having that current experience a drop in voltage of 100 volts. In both cases, that delivers 100 watts. You have to design the light bulb there are different light bulbs. You won't use the same ones. So far, we're okay? All right. So what Edison started about doing was going to higher and higher voltages. The current was a problem for him. He couldn't deliver vast currents without the wires just gobbling up his power. So instead, he made the difference in voltage between the two delivery wires, the one that the current arrives in and the one that you send it back to the generating plant in. He made the voltage difference between those two wires as big as he could. There's a limit. You just can't. You can 12 volts, easy sneezy, pretty safe. 120 volts, that's getting to be a little hazardous. You don't want to touch those wires and become part of a circuit. It will bite. 1,000 volts, whoa, dangerous city. That's not only is it bad to touch. I mean, that would be really bad to touch it. It will drive huge currents through you very easily. It's likely to send currents through all kinds of paths you didn't expect. Burn spots in wiring or in your house, or basically you start fires all over the place. So he went to as high a voltage as he could go to without being obviously unsafe. Now, surely some number of house fires and such were caused by using voltages that were a little too high. All right? Well, what are you going to do? He was at that point stuck, and I'm going to skip this. It's not even a very good question. Okay, so what happens then is instead of trying to deliver the power from the generating facility to the consumer in a single circuit, people decided, and the people really are Nikola Tesla, the origin of the name of the car. Tesla was he Croatian or Serbian? I can't remember. I never remember. Serbian. Inventor, and he was backed by George Westinghouse. Westinghouse used to be a household name. I mean, a house, yeah, house. Westinghouse was in my youth, Westinghouse was everywhere. At this point, it's kind of, you barely hear about it anymore, but he had made his fortune with inventing things for trains. So George Westinghouse backed Nikola Tesla, and Tesla had a different idea. Instead of imitating batteries and sending power in a single circuit from the battery or equivalent thereof to the consumer, use alternating current, and we'll see what that is in a minute, and send the power from the generating facility, the battery equivalent, to the consumer through a series of separate circuits, moving power from circuit to circuit to circuit as necessary. And what this allowed them to do is to use sort of a hierarchy of power delivery stuff. So when you, where do I want to do it? You would generate electricity at some relationship between current and voltage. We'll leave that for the moment. But the first thing you do is you deliver the power, and I'll talk about that shortly too, to the long distance transmission circuits, the wires associated with this long distance transmission circuit. Those wires operated with a very large voltage difference between them. So you were putting lots of energy, you were making available lots of energy per charge in moving from the high voltage wire to the low voltage wire. The voltage difference was so huge that every coulomb of charge that made the transition would give off gobs of energy. And therefore, you could use relatively little current to deliver a lot of power. So the high voltage transmission circuits that go across the country, their concept is the wires can only handle, let's say, 100 amperes. Well, if you have only 100 amperes to deliver power through two wires that differ in voltage by only 12 volts, all you can deliver is 100 amperes times 12 volts. That's 1,200 watts. That's enough to make one person's toaster or hairdryer work. But then you're done. So what are you going to do? Don't use 12 volt difference. Use 12,000 volts or 120,000 volts. So let's just jump up to 120,000 volts. If you've got 120,000 volts and still 100 amperes of current flowing in those wires, because that's all they're really capable of handling well, that's 1.2 million watts of power delivered. That'll run a small community. So go to very high voltage differences. That allows you to deliver a lot of power without needing a lot of current flowing in the wires. When you get to a city, 120,000 volts, and actually they go way beyond 120,000 volts. They go to 500,000 or even 1 million. When you get into a city, you don't want that kind of voltage around. You probably have noticed that birds don't perch much on the high voltage, the really seriously high voltage wires. They'll perch happily on the local stuff. And you might, it's instructive to think, why can a bird just perch on the wires delivering power to your local community? Those wires are not insulated. They're just bare metal. And so the bird's got a hold of it. Well, it's not part of a circuit. So when that, suppose there's plus 1,000 volts on that wire, when the bird first touches the wire, charge goes onto the bird now is 1,000 volts also. But beyond that migration of charge onto the bird, the charge just sits there on the bird, doesn't do anything. And the bird is now high voltage, but big deal. So 1,000 volts, not such a big deal. 500,000 volts, bigger deal. When the bird touches that, the charge that goes onto the bird and subsequently leaves the bird through any sharp point by way of coronal discharge and stuff like that, evidently not pleasant. So birds don't perch on those super high voltage wires. Yeah. How much voltage is lightning? It's probably on the order of like 100 million volts, something like that. Just tremendous voltage difference. Enough that the electric field is sufficient between the cloud and the ground. The voltage difference, if it's 100 million volts or something like that, the electric fields along the way are enough to push push any electric charges in there that are present in the air and accelerate them, make them go fast enough that when they hit other objects, like other air molecules, they knock charge out of those, which knock charge out of other ones. So you get this catastrophic spark that's caused by a huge electric field from that giant voltage difference, and all the little charged particles just cascading against each other as they're being pushed by the electric field. They smash into each other, and then you end up with this vast, this channel of basic conducting material. It's a mixture of charged particles. Okay? Yeah. So I will show you before we go, a couple 100,000 volts. When you can do it now. So just to finish this thought, because we want to, I want to leave you with something meaningful with this, that if you can convey the power long distance as a modest current with very large difference between the delivery wire voltage and the return wire voltage, you can make the current travel without losing a lot of its power en route. You don't want to deliver the power at that voltage. It will start sparks and everything in everybody's house. So instead, you move the power from that circuit without moving the charges. You move the power into a second circuit that operates with a larger current at lower voltage. So now you have to deal with thicker wires to carry it, but that's okay because they're short. And you use thicker wires, and the voltage is lower, safer. So that's what's happening with all these transformers, is power is moving from circuit to circuit, and the relationship between voltage and current is one value in one circuit, and between voltage and current in the other circuit, it's different. So the way you move that power is by way of a device known as a transformer. I'll give you a little introduction before I turn on that one. A transformer, boy, I mean, 1,000 things to talk about. This is a circuit. It's a coil of wire with a light bulb in it. I'm going to do this as mystery theater here. It's like, okay, I'm going to do a fun and games. I have to explain to you next time why this is going to work. I'm going to run a current through this wire, making this an electromagnet. Remember, currents are magnetic. This will become magnetic. But the current in this electromagnet doesn't go constantly in one direction. It reverses direction many times per second. In this case, it goes over and back 60 times per second. It's known as 60-cycle alternating current. Therefore, the magnetic field around this iron bar will go up, back and forth. It goes from north pole up to south pole up, north pole up, south, north, south, very fast. Fluctuating magnetic field. It turns out changing magnetic fields are themselves electric. I got to add that entry to the table I've been building up on the view graphs, but I'll do it next time. The point is, there's an electric field around this fluctuating magnet. And if I put wires in the presence of that electric field can push current through them and light the light bulb up. No electrical connection. Two completely separate circuits. No charge moves from one to the other. Okay? I mean, the fun toy version of this. This is another circuit. It's just a single turn of aluminum. That's all it is, a ring. And when they run this guy, that guy has current flowing in it, and technically what happens is a little complicated, but they repel each other like that. Woo! Okay. So having shown you that, so, because you always ought to, it's a rainy day, I have to do something fun. This is a transformer 2 in which we're going to run an alternating current through the coil that's down here at the bottom that has 8 visible windings of metal. So the current will flow first one way and then the other. And for technical reasons, the reversals occur something on the order of 1,000,000 times per second. And that will create a magnetic field, and the magnetic field is fluctuating north pole up, south pole, north, south, really fast. And that makes an electric field. The electric field will push charges in this coil of wire. They'll push it first up, and then as things reverse, they'll push it down. This guy is going to have charges pile up on there like crazy, to the point where it reaches hundreds of thousands of volts of it'll be 100,000 volts positive, and then it'll be 100,000 volts negative, back and forth. The reversal process involves a spark gap, which is very loud. I've actually not watched this guy operate. I made one myself long ago. We used to show that, but this is the first time I'm showing the commercial one. So it's going to be sound as the spark gap is firing. Okay, I'll hit the light so you can see it properly. Yeah. Yeah. Oh, get those guys out of here. Okay. Here you go. Incidentally, the electric fields associated with that are so strong they can push charges around in a light bulb. All right. Fun and games. The one I built, I wouldn't put my fingers in it. I could let the current go through me. This one, that looks a little too intense. I'm not going to let that one send current through me. It's very high voltage, but the currents involved are very small, and because they're high frequency, they tend to go over your skin. So they typically aren't dangerous, but they can give you burns because they put a lot of current through the very surface layers and stuff. And that, anyway. So have fun in the rain, and see you on Friday.